Okay, yes. So the first order of business, as Adam says in the chat, the backstory to this talk is a year ago, for some reason. I can't remember why anymore, but today is Alex Menon and Alex Dobner's birthday. So I made a promise a year ago that I would give a talk to celebrate. So I delivered on that promise. You can ask Ben. I scheduled the talk like literally a year ago. So everyone needs to wish Alex and Alex a happy birthday.
Thanks for giving this talk, Jeff.
You're welcome. I would have been pissed if you didn't come, so I'm glad you're here.
Did I misunderstand? Are we not singing?
Maybe afterwards. How about that?
Okay.
We can do it afterwards. So the other order of business is just some preliminary comments. I'm going to try to be pretty faithful to the reference text that I'm going to be basing this talk off of, which I'll share with everyone at the end of the talk. It's good stuff, so you should all read it on your own time. But maybe to be faithful to the reference text, which was not written in LaTeX, I'm giving a slide talk, but not with Beamer, because LaTeX is for sheeple who are brainwashed by the mainstream math media. So I made just a regular PowerPoint presentation, or it's a keynote presentation, but I think you'll find that it's vastly superior for giving technical math talks than Beamer. So I highly recommend it. Also, because I'm going to be so faithful to the source material, in particular, a lot of the slides are just kind of screenshots of the book. You may at times be worried that I'm having a stroke, but I promise you I'm not prone to strokes, not yet at least. So don't worry about that. Oh, also, because this is such a serious talk, and I want you to take me really seriously, I'm just gonna add a filter. Pigs are pretty serious, so. Okay. Feel free to ask questions at any time too. So, we'll begin. Now, as with all good math topics, I want to start off with the motivating question. So, fact. Turns out that NASA admitted that when they landed on the moon, they had computed a trajectory, but they missed the spot by 20 kilometers. What's up with that? That's ridiculous, right? NASA is supposed to be full of really smart engineers that are good at math. I'll tell you what's up. That's right. The value of pi is wrong. That's what this talk is about. The traditional 3.14159, it's all nonsense, and I'm gonna prove it to you. The true value of pi is a little bit bigger. So this is the goal of the talk today. So indeed, here's an excerpt. So source of information claim that NASA is secretly using another value of pi, which is a bit bigger. And the story goes that the moon craft would have missed the moon if they used the traditional value. So to correct for that, they had to increase the value of pi to actually land on the moon, you know, if it actually happened. Like, I don't know if anyone really believes that, but anyway, so this is kind of hard, rock solid evidence for the fact that the traditional value of pi is pretty fishy. If you want some more evidence, another source that the author gives is from a guy named Billy Meyer, who is a Swiss farmer. Evidently, he's maybe not a terrestrial being or something like that. It's maybe not so clear, but He's in the know for sure, so he knows the stuff. And here's what Billy says. So the pi is miscalculated, and by eliminating this error and correcting future computations based on pi, scientists will have the capability to make unimaginable energies accessible to the people of Earth. This will be accomplished through the terrestrials' diversion and utilization of energies from black holes. So think about this. This is really serious stuff. This is a big deal. If only we changed the value of pi by just a teeny bit, we could start harvesting the energies of black holes. We've essentially stunted the growth of humanity by using a slightly wrong value of pi. So this should tell you like how big of a deal this is. And so I'm giving this talk to spread the word, because the more mathematicians that know the truth, the better. Indeed. I know you're laughing on the other side of the screen, but everyone laughed at flight. And I'll tell you that in 10 years, when I have personally harnessed the power of a black hole and begun dominating the Earth, you won't be laughing. Anyway, so that's the introduction. This is what we're talking about. Pi is wrong, and the goal of the talk is to convince you of this and to tell you what the true value of pi should actually be. So because this is going to be a technical and difficult talk, I want to begin with some review to make sure that we're all on the same page, some background material. The first is, so the value of pi, what should it be? It should be the number of times that a circle's diameter wraps around its circumference. So here's a picture. So the diameter is this guy. Circumference is the whole thing around the circle. And if you take the diameter and wrap it around the circle, you should get about three and change times. So that's what pi should be. Now, this is the first red flag. Think about this. So this is sort of an abridged quote from the book. But the traditional value of pi is sort of obviously ridiculous because you're using a straight line, the diameter, to measure something which is curved. That's absurd. It makes absolutely no sense. And like I said, this is sort of the first red flag to suggest that the traditional theory of pi has to be nonsense. Why would you do such a thing? Why would you measure a curved thing with something straight? Makes no sense. Okay, so what's the truth? The truth is that there is a deep relationship between pi and phi, the golden ratio. So let me remind you what phi is, because this will be really important. So phi, the golden ratio, there are various ways to define it, but turns out that it's 1 plus the square root of 5 over 2. Okay. So most of this talk is going to be to develop the relationship between pi and phi to uncover what the real value should actually be. Anyway, that's phi. Now, as some more evidence that there's sort of a cultural bias against phi, you can't do that on Beamer, can you? If you pull out your scientific calculator, which we all have and use all the time as math PhD students, pull it out next to you, you see a pi button, you don't see a phi button anywhere. That's ridiculous. So this is evidence of corporate bias against phi in favor of pi. Like I said, this is a big deal. Now, I reviewed what phi is. And because most of the talk will be about phi, there's some more important background material I need to give you. So for example, the author says, for your memory power, it is good practice to learn the following powers of phi to at least 3 decimal places. So if you're really smart, you can learn them to 9 decimal places, but most of you probably aren't smart enough to do that. So 3 decimal places should be sufficient for most of this talk. So yeah, I'll give you a second. You can quickly memorize these. And I guess the 9th power maybe isn't so important. I don't know. Maybe he just forgot to fill out the table. But the first 8 powers are up to power 8 at least. Okay. Chris's friend Lucas also has a birthday today. Happy birthday, Lucas. Any questions about this slide before we move on? Okay, so like I said, we want to start understanding the connection between pi and phi. So I've included a couple sort of heavy sentences from the text that we'll start to unravel. But let's see, so maybe let me highlight some important points. So the following information, simple enough for any teenage student to understand. It needs to be said that this rare information is basic knowledge, but is advanced knowledge in the sense that we need to already know this concept of the golden mean or phi proportion and the root of 5, pretty good, as well as pi, which is simply the relationship of the unity square to the circle circumscribing it. So that's a pretty technical sentence. I'll explain this as we go along. So when he says unity square and the circle circumscribing it, this is what he's referring to. So first of all, unity square is another technical term. This means a square with edge length 1. So this guy right here, that's a unity square. And what you can do is you can draw a unity square and then draw a semicircle around that. And you get phi. So this is a bullet of fact. And this is the key to, one of the keys to the connection between pi and phi that we'll start to uncover. And yeah, so the true value, as we'll see, is called Jane pi, named after the author himself. So as a heads up, whenever we say Jane pi, that's what the true value of pi should be. Okay, so there's the unity square. So let's see what's next. All right, so the realm of intuitive mathematics would state clearly that if a unit square inside a semicircle generates phi, then surely that same unit square inscribed in its own circle, whose circumference is that which we call pi, the fundamental connection between all circles and squares with the same diameters or side lengths must be rooted in phi ratios. Obviously. Now, where it gets interesting is when we start considering a double unity square. So this is another technical term here. But so a double unity square is two unity squares on top of each other. I'll show you a picture here in a second. But before that, so you probably already know that ancient cultures like the Egyptians had priests who placed their sacred objects in an altar that were based on double cubes. So I was talking about unity squares, but there's also a concept of a unity cube, which is a cube with edge length 1. And so a double unity cube is apparently a pretty big deal. Holy form incubates the divine proportion, and it's our starting point to go unlimited. So we need the cube or square, the form or limit, to become formless and unlimited. To show principles of mathematical time travel. So like I said, this is really important, and we can uncover some crazy stuff with the true value of pi. Okay. All right, so here's a picture of the double unity cube. So in the previous picture, we just had 1, and then we had a semicircle. But if you put two unity squares together, you get a whole circle. And a circle is pi, right? Now, here's where you really start to see the connection. So with a double unity cube, it turns out that this diagonal length is the square root of 5. I'll prove it for you, don't worry. So let me show you the proof. Oops. So here's the proof. So it's based on a result called the Pythagorean theorem, which is right here. This is sort of the clearest way to state the Pythagorean theorem. The square on AB, so that's referring to this length squared. The square on BD is this length squared, is the square root of, or the square of those, the sum of those squared is the length of this squared. In other words, in more conventional notation, if you call this distance x, you get this, and then you can do some algebra to solve for it, and you get square root of 5. Okay, so what's the point? Phi had a square root of 5 in it, right? So we're starting to see how pi circle is related to phi, because we clearly have a square root of 5. And as Jane points out, there's something really special about this, as you will see, in the sense that we have anatomically 5 fingers and 5 toes, as if this was some template of creation. So pretty deep. Anyway, so the summary so far is that the square root of 5 is the key to both phi and the true value of pi, which in decimal form is this right here. And I'll show you soon where this comes from. Okay, so let's see. The next important step is to study the square root of 5 to 2,500 digits. So I'll let you behold this for a few seconds. It's good stuff. Okay. Ewan's got it down. So now that we're experts in the square root of 5, I want to start uncovering the relationship between pi and phi even more with a technical technique called the fairy wand method. Sometimes in the literature, it's referred to as the lollipop method, but most experts in the field call it the fairy wand method, so I'll go with that. And this is an even deeper analysis of the relationship between phi and pi based on this double unity square circle picture. So here's what the fairy wand method is. Okay, so take that picture from before with the double unity square, and then rotate the double unity square 90 degrees. And you can sort of start to see the fairy wand appearing. And then you add a handle of length 1. Then, so if you recall from a few slides ago, this has length √5. The handle has length 1. So 1 plus the square root of 5. Okay, so now we're getting closer to phi, right? Right, so this picture explains where 1 plus the square root of 5 comes from. Now, a good question is, well, Joe, the phi is 1 plus the square root of 5 divided by 2. So where does the divided by 2 come from? Well, the fairy wand method tells us about that as well. So if you, yeah, I couldn't find the divided by sign. So in the fairy wand method, so we have this √5 and then this handle of length 1. When you take the double unity square and rotate it, that cuts out another sort of central unity square. And you can draw a circle in that, right? It turns out that when you draw that circle, it intersects the halfway point of the whole handle. That's where the divided by 2 comes from. So I've got a circle here, another circle here. So there's like 2 instances of pi, roughly. And then this handle of length 1 plus √5. And this central circle intersects the midway point. So this is the fairy wand method. Oh, nice. I didn't know that. Well, no LaTeX in this talk. This is a real math talk. Anyway, so the other cool thing about this text is that there are all these rare pictures of like original, hand-drawn work. So this, I think, was maybe perhaps the original document where he discovered the fairy wand method. So, good stuff. Look at that handwriting. Can't be wrong with handwriting like that. Thanks, Clark. Thanks. Okay, so I have some other figures of the fairy wand method. I didn't think about copyright infringement. Hopefully not. So that's another good one. Here's a slight variation on the fairy wand method where the handle is straight. And then as Jane says, essentially this geometric fairy wand method clearly confirms that the essence or structure of pi is phi. Thus, the recrudescence of phi pi. I had to look that word up because I had no idea what that means. So I did that for us. It means the recurrence of an undesirable condition. So I don't know if that's the word maybe he was going for there, but that's okay. I learned a new word, so. Okay, so if you're like me, so the thing about this book is it's literally 200 pages long. I've looked through all like 200 pages of this book, and there's clearly a ton of evidence, a ton of geometric evidence that there's a deep relationship between pi and phi. So I'm pretty convinced, and you should be too, that the traditional value of pi is wrong. But the good question is like, well, what is the correct value, and what's the proof? So, excuse me. Like I said, after looking through over 200 pages of this book, I think I basically boiled down the point, and I'll show you the relevant part in a second here. But here's my formulation of like the proof that pi is wrong. So this is sort of the technical apex of the talk, I think. So hopefully you guys can follow along. Okay. So step one is to note that the square root of phi is 1.272019649. If your scientific calculator had a phi button, you could verify that, but you can't. So you'll just have to trust me for now. But that's what the square root of phi is. That's the first step. Second step, note that 4 divided by pi is 1.273239545. Okay. That's crazy, right? Square root of phi is suspiciously close to 4 divided by the square root of pi. Okay. So here's probably the hardest step. So this is actually, so when I say pi, good question. When I say pi here, this is traditional pi. So this is like 3.14159. Good question. Okay, so this is probably the hardest step. So if you do some algebra, which if you want, I can do for you, if it's too difficult to do in your head, but if you rearrange this a little bit, you get that pi is very close to 4 over the square root of phi. Okay. And the point is like, that can't be a coincidence, right? Obviously. So therefore, the correct value of pi should be 4 divided by the square root of phi. Proof. So I'll let you soak in this argument for a second because it's pretty difficult. But like I said, after reading like 200 pages of this book, I'm pretty sure this is basically the point. Yeah, so that's a good point, Jerry. Pi is an algebraic number. The real value of pi is, at least. Right, so the double unity squares, as far as I can tell, what I gathered was that the fairy wand method was sort of just geometric evidence for the relationship between pi and phi, but the actual hard, like indisputable proof is this, I think. Like I said, I encourage everyone to read through the book yourself after the talk to take from it what you can. Anyway, so like I said, this is my formulation of the proof. I think this is sort of the key page in the book where he goes through this. So this is Jane's version. So we can see he gives some more exposition, it's never a bad thing. But so if you were to divide the traditional value of pi by 4, and so maybe a good question is like, why would we do such a thing? Why would I divide 4 by pi? And it's because what you're really doing there is you're examining the shape of the square. So the unity square has perimeter 4 by the shape of the circle. Circle with diameter 1 has perimeter pi, right? Anyway, so you divide that, you get this, which is remarkably close to the value of square root of phi. So I think this is the proof. And he also points out the interesting perspective that we alternatively could have arrived at this by looking at this formula for the area of a circle, right? Because the radius of this circle is 1/2. So the area of the square is pi divided by 4. Anyway, I think this is the relevant page. Like I said, my formulation on the previous page is the one that makes a little more sense to me. But take from it what you will. Okay, so now that we know the true correct value of pi, we've gone beyond the realm of the rational and are now accessing our higher intuitive mind. The part that knows that Jane pi, the true value, is 4 divided by the square root of phi. Okay, so as with any good theorem, we need some good corollaries and applications. So the rest of the talk, I'm just going to spend some time talking about some implications of this. So here's the first interesting corollary that Jane proves. It's a little confusing to look at, so I'll help you interpret it. But so the corollary, let me kind of highlight it here, is this guy. And what's confusing about this is that he uses pi when he really means Jane pi. So I don't know why he did that. But the corollary is that, yeah, so I'll get to that, Alex. We'll talk about moon landings again soon. But yeah, so the corollary is that 4 times the square root of phi is phi times Jane pi. So that's pretty amazing. And so what's the proof? So the proof is, well, by definition, Jane pi is 4 divided by the square root of phi. And if you need that verbally, he's got it for you right there. And in other words, you can write it as a fraction. Then you can multiply the square root of phi to the other side, and you get this. And, you know, just to clarify, you may think this is like a right group action or something, but this is just the dot represents multiplication. Anyway, so that's the first step. And then to get rid of the square root sign, you multiply both sides by the square root of phi. And so then the square root of phi times the square root of phi is phi. And then on the left, you get 4 times the square root of phi. And then as desired, we have this really interesting corollary. Any questions about that one? Let's see. Okay, so here's another pretty interesting thing. So one of the things that Jane does is he starts comparing high powers of pi, of traditional pi and Jane pi. Because, you know, you might think like, okay, traditional pi is 3.14159. Jane pi, turns out, is like 3.1446. Like, that's not a big difference, right? So it probably doesn't make a big difference at the end of the day. But the point is that if you start raising these to higher and higher powers, look at that, then the difference really, really becomes clear, right? So you can see how big of a difference this is. And so he says, you know, so this kind of explains the whole NASA moon landing phenomenon, because this is actually a big difference, especially if you are using the mathematics of pi to navigate satellites and space probes. So if you raise these to the 10th power, the difference is more than 1,000. And then he says, so the shocking revelation is that if you raise them to the 16th power, it's over 1 million. That's crazy. And presumably, I'm not sure, but presumably if you kept going, if you raised it to even more higher powers, the difference would just get even bigger. So that's pretty crazy. Yeah, so Cecilia is a good question, which is what is the meaning of the red triple numbers? And, I think if you don't understand, then you just probably won't understand. So what's confusing is that, like, in some of these pictures, it's just like 3 repeated numbers, but in other pictures, he's highlighted in red things that aren't just 3 repeated numbers. So it's pretty deep. I don't know. We'll see. Okay, so that's pretty interesting. Oh, did Alex find a triple that wasn't red? Let's see. Yeah, good eye. There's a 333 here. I mean, so that's obviously not a mistake. Obviously that was intentional, and we probably just don't understand, right. So, oh well. Some things we just won't ever understand. Okay, right. So here's, so we know that the true value of pi is 4 divided by the square root of phi. And something that's really important to do is to figure out what this is to 1,000 decimal places. So here it is. Again, we have more highlighted numbers. So what's interesting is that, like, here, this is just a highlighted sort of repeated pattern. This is pretty wild here. So there's some really interesting ones here. So yeah, I'll let you soak this in for a second. Now, what's interesting about this, and so this is another cool aspect of the book, is that, I think we all know that math is really hard and working in isolation is difficult, and collaboration is a key to success and to proving the theorems and stuff. So in the book, he has a lot of examples of correspondence with other people, and you can kind of see the progress in action. You can really see research being done. And so this is an example of this, actually, this 1,000-digit computation, like no one man can do that alone. You really need a collaborator to help you out with that. So one of the interesting things is, yeah, he has an example of a correspondence. So one of his collaborators made another fascinating observation that Jane pi can equivalently be written as the square root of 16 divided by phi. And so I think for the sake of the author's privacy, he doesn't include the email that was sent to him, but he does include a response about this revelation. So he says, let's see. So, hi Jepsita, I like the way you express the true value of pi by squaring the fraction of 4 over root of phi, giving this expression, or this. That's really cool. Can you send me the value of 3.144 to as many decimals as possible using the Wolfram site, or were you giving me this link so I could do it myself? I would prefer that you can send the result. So presumably in Jepsita's email, it sounds like she sent him a link to Wolfram Alpha or something to compute Jane pi to many digits. But, you know, Jane's a busy guy. He doesn't have time to do all that himself. So, but I think what Jepsita did is she did send him successfully sort of longer decimal computations for Jane pi. So like I said, you can really see the collaboration kind of in progress leading up to the impressive thousand digit computation. So like I said, that's an interesting example of collaboration. Here's another interesting one. So this is from Oleg of Ukraine, and he noticed a really interesting pattern. If you write out Jane pi, pi, e, and phi, in the 12th decimal place, they're all 9. That's pretty crazy. He doesn't say anything else about this, so I'm sure this is an active area of research. He's probably studying this, yeah, for volume 9. So I don't know. Pretty fascinating connection. Okay, so here's one of the main applications I want to talk about for the sake of this talk. So this will be the last maybe application, and then I'll give some parting remarks, and then that'll be it. So the application is in the analysis of crop circles. So, for example, here's a crop circle that appeared at Barbary Castle, I think in 2008. Let me write that date down so you don't forget. It's pretty amazing. Okay, well, what's the deal with this? This crop circle is a visual representation of the traditional value of pi. So here's what's happening. So let's see. So here's the actual picture. And then there's a dot here. Oh, sorry. There's a dot here. And if you divide this into sectors, here's the way you read this. This first thing is 3 sectors long. So it's like 3.1 sector, 4 sectors, 1, 5, 9, etc. So this represents pi, pi, the traditional value. So here's some other figures to explain what I just explained. And he also points out that so these 3 circles at the end, here, here, and here, he believes represents the 3 dots to signify that this expression of pi really goes on forever. And for what it's worth, often in mathematics, we place 3 dots after a transcendental number to indicate that it travels to infinity without detectable symmetry. So that's that. Anyway, like you guys have pointed out, this is the wrong value of pi. So what's up with that? And what Jane says is that when the time is ripe, a similar crop circle will appear like this, but with the corrected harmonically tuned numbers of Jane pi. So let's talk about the Jane pi crop circle, which, just to clarify, has not appeared yet. It will one day. Mark my words, it will, but it hasn't yet. And so Jane has some figures that depict hypothetically what the Jane pi crop circle will actually look like. So here's one figure. What's kind of interesting about this is that Jane decided to design this crop circle from the outside working in. So like here are the sectors again. And the first big one is 3. The decimal is over here this time. And then 1, 4, 4, etc. He doesn't really say why he made that choice, so I probably just don't quite understand, but you know, it's interesting. And then here's another really rare hand-drawn version that he includes. So this is pretty fascinating to look at. Here he says, so this is the implosive stargate, or entry point into the wormhole, physics of black holes. So you remember earlier when we were talking about Billy Meyer referencing, you know, harnessing the energies of black holes and stuff. I'm assuming what's going to happen is that one day this Jane pi crop circle will appear, and apparently it might be like an entry into a wormhole, or it'll be the stargate that lets us actually harness the power of black holes. So. Oh, right. And so the other thing that he includes is this other crop circle, which, you know, has sort of a similar form, but it's sort of unclear what it is. So he says this has concentric rings and may be another form of coded cosmic mass. So the point is, crop circle mathematics is an active area of research. So if any of you can figure out what this one represents, you should probably email Jane to let him know. Good stuff. Okay, so that was the last main application that I was going to talk about, was how Jane pi applies to crop circle mathematics. So to finish off, before I give some parting quotes, one thing to advertise is that there's going to be an international Is Pi a Lie conference. And I don't know when it will be, but one day it'll happen. Here are all the speakers. I'm going to go ahead and pencil my name in as well. So watch out for that. Stay tuned. It'll be a big deal. And okay, so to finish this off, I just want to give you some quotes, and then I'll drop a link to the book in the chat in case you haven't actually found it. Because like I said, it's good stuff. Everyone should read it yourself. So here are some maybe parting motivational quotes from Jane. Okay, so I present this fascinating material merely to inspire, to look a child in the eye and silently instruct them to remain connected to their intuitive mind, to explore their deepest imagination, to grok the true physics of time bending based on the true phi pi celestial transcripts, to see mathematics as a star language and numbers as anointed living entities, to recognize that every living protein in your body is pentacle shaped, to learn how to repent the philosophy, I like that one a lot, of love, and of course, to transcend or go beyond the hex sex. I can't say I quite followed the last part, but it's pretty deep, makes you think. And then here's another good one. So Jane pi is purification. Traditional pi is dirtification. Or to say it bluntly, modern mathematics today, whose God is traditional pi, takes our budding students down a cul-de-sac, whereas the true ancient phi pi harmonics of Jane pi literally transports them onto the highway. Pretty wild. Okay, that's the end. I'll stop recording and then you can ask questions.